All right, kiddos, welcome back. And we're continuing our discussion on Voltaic cells. Remember, we were talking about electrochemistry and Voltaic cells. So we're just going to work through a few examples, and I think as we do these, you'll pick up on this pretty quickly. It's actually one of the easier things, I think, that we do this year. So for example 3, I'm going to give you pairs of half reactions. So if you can imagine these occurring in 2 beakers. So if I could draw a picture just to remind you off to the side. Here's 1 beaker, and they're connected by salt bridges. Do you remember the purpose of a salt bridge, kiddos? Yeah, it's to maintain charge neutrality between the 2 half cells. This first beaker looks like it has platinum 2+ ions in it, and a piece of platinum metal, so we'll make that this electrode. And the second beaker looks like it is made out of, or the electrode's made out of tin, and it's in a solution of tin 2+. Let me just make sure. Yep, tin 2+. And we're going to have a voltmeter between the 2 cells to measure the voltage that we end up when we find the oxidation and reduction potential from both cells. So remember, to do that, it looks like you're given 2 reactions that are both reduction reactions. We have Pt2+ plus 2 electrons, and that's making platinum, folks. And the other one is tin 2+ plus 2 electrons as well, and that's making tin. Well, you know that both of these cannot be reduction reactions. One of them has to be oxidation. So how do we determine which one's reduction and which one is oxidation? Very good. We're going to look up their individual reduction potentials. And whichever one has the higher reduction potential, of course, will be reduced. The other one, we're going to have to write the equation backwards and find its oxidation potential. So let's look these 2 up on our reduction potential chart. So we have platinum 2+ becoming platinum and tin 2+ becoming tin. So we have to scooch back a couple of pages here, kiddos. So let's see if we can find those 2. And once again, these are not alphabetized. They're listed in order of reduction potentials. So looks like I found my tin first. Here's the tin 2+ plus 2 electrons. That's negative 1.38. And the platinum one, let's see where that might be. Here it is. Here's the platinum 2+ becoming platinum, and that's a positive 1.18. So negative 0.138 for the tin and positive 1.18 for the platinum reaction. So let's scooch back over now. We're going to write those 2 down. And so the platinum, as you recall, had a reduction potential of positive 1.18, and the tin was a negative 0.138. Now it's obvious that the platinum 2+ has the higher reduction potential, so we're going to leave that equation as it's written, and the tin equation we're going to write backwards. So we're going to go ahead and erase this, and we're going to have tin becoming tin 2+ and 2 electrons. Now that's oxidation, so we change this sign to a positive 0.138. Now let's add these 2 equations together. 2 electrons gained and 2 lost cancel each other out. So we have Pt2+ and tin on the reactant sides, and we end up making tin 2+ and platinum on my product side. And let's see, the overall potential would be the sum of the individual potentials. So we're going to have 1.18 plus 0.138. And we'll round that off to the nearest 100th, and I get positive 1.32 volts. So let's see, I've written the balanced equation for the overall reaction. I've calculated the standard cell potential, and now we're going to describe the reaction using this shorthand or abbreviated cell notation. So to do that, we'll put the 2 vertical lines here. And on the left side, we'll write the oxidation reaction, and that was tin becoming tin 2+. And then the reduction reaction was platinum 2+ becoming platinum. All right, so since this platinum was reduced, that's my cathode. And the tin was oxidized, that's my anode. and the electrons will move from the anode towards the cathode. And as they do that, my voltmeter should give a reading of 1.32 volts. Those moving electrons now we can put to work. And in this case, it's just operating our voltmeter. Okay? All right, how about if I do one more for you, and then you try to do one on your own? All right, so letter B, looks like we have cobalt 2 plus is gaining 2 electrons to become cobalt. My other option is chromium 3 plus gaining 3 electrons to become chromium. So let's look up those two reactions. Once again, we have the cobalt 2 plus and the chromium 3 plus gaining electrons. So we have to go back a couple of pages to my reduction potential chart. We have to search for those, unfortunately. So let's see what we find first. There's chromium 2 plus right there. That doesn't help me. Oh, here we go. Here's the chromium 3 plus gaining 3 electrons to become chromium. And that is a negative 0.744 volts. And my cobalt 2 plus gaining 2 electrons to become cobalt. Let's see if we can find that. Here we go. That looks like that's a negative 0.28 volts. So now we can go back over to this page. We can write those down. The cobalt 2 plus 2 electrons was a negative 0.28 volts. And the chromium 3 plus 3 electrons was a negative 0.744. Once again, we'll just go to the nearest hundredth to make life a little easier on ourselves. So which one has the higher reduction potential? Yeah, it looks like the cobalt 2 plus does. So negative 0.74 is obviously lower than negative 0.28. So we're going to take the chromium reaction and erase that. We're going to have to write it backwards. So it'll be chromium becomes chromium 3 plus 3 electrons, and I change the sign to a positive 0.74. Now I can add these reactions together, but this time it's not going to be quite so simple because we have 2 electrons gained and 3 electrons lost. Those need to balance. So what I'm going to do is I'm going to multiply this reaction by 3 and this reaction by 2, and that'll give us 6 gained along with 6 lost. So I will have 3 cobalt 2 pluses and 2 chromium metals becoming 2 chromium 3 pluses and 3 cobalts. So I have a 6 positive charge on the left and a 6 positive charge on the right, 3 cobalts on both sides and 2 chromiums on both sides. Now we can add those potentials together, and for this one we have a negative 0.28 plus a positive 0.74 for an overall potential of positive 0.46 volts. Okay? All right, go ahead and try letter C without my help, then come back to the video. We'll see how you did, okay? Alrighty, welcome back. We have 2 reactions here, Hg2 plus and 2 electrons are going to make mercury, and Cr2 plus and 2 electrons will make chromium. So we need to look up both of those half reactions once again, and we'll decide which one has the higher reduction potential. That'll be the one that's reduced, and the other one will be oxidized. So let's search and search and search, okay? Let's look for the simple mercury one. And let's see. That's not it. Let's see. That's mercury 1. I have mercury 2. And I cannot find that potential. Where is it? Help me out, kiddos. Do you see it? Here it is. I went right by it a couple of times. You probably found it and were yelling at the video, weren't you? So it's positive 0.851. And let's look up the chromium 2 plus becoming chromium. There, I found that one fast, didn't I? That's a negative 0.913. All right, so now we'll go back to our 2 reactions, And we're going to write those potentials down. The mercury one was a positive 0.85, and the chromium was a negative 0.91 volts. So it looks like we're going to erase the chromium one again, because this one has a higher reduction potential. It will be reduced. So let's erase the chromium reaction and write it backwards. So that will be chromium becoming chromium 2 plus 2 electrons, and we'll change that sign to a positive. Now we can add these up. This is easier than the last one. Those 2 electrons gained and lost cancel. So we have Hg2 plus and chromium metal becoming chromium 2 plus and Hg, and both the atoms and the charge balance. So we can add those potentials together. 0.85 plus 0.91, both of those are positive, and I get a 1.76 volt battery this time. Now I didn't write the cell notation on the last example or this one, so let's do that quickly. We have our 2 parallel lines. The oxidation reaction was chromium to chromium 2 plus, and the reduction reaction was Hg2 plus to Hg. Let's do the one up above. I just left that blank. I apologize. Here's our two vertical lines. We have chromium became chromium 3 plus. That's my oxidation, and cobalt 2 plus became cobalt. Alrighty. You getting the hang of this? How about this time I give you the abbreviated notation, and then we figure out the balanced chemical equations for these from that standard cell notation. Yeah, this sounds fun, doesn't it? All right, so let's see. We have I negative, and that's turning into I2. To balance this, I'm going to put a 2 in front of the I negatives to give me 2 iodines on both sides. They're negative 1, so I need to jettison or get rid of 2 electrons. The other reaction is Fe3 plus, and that's becoming Fe2 plus. For that to happen, I have to add an electron, don't I? All right, let's look up these potentials. I'm going to look up the one on the bottom first, because that is reduction. And I can just write that down directly. So Fe3 plus to Fe2 plus. Let's see if we can find that. Fe3 plus to Fe2 plus. Let's see here. Once again, you're probably screaming at me saying, Hummer, it's right there. Open your eyes. So it looks like it's right here. Fe3 plus plus an electron makes Fe2 plus. And that is positive 0.771, and then the other one, I forgot what it was 2I negative. The other one, let's see, this is oxidation here, isn't it? So we have to look for the backwards reaction, don't we? So let's look for I2 plus 2 electrons becoming 2I negative. Oh, here we go, that's right here. And now that's positive 0.536, but we're going to have to change that sign, remember? Because we have the 2I negatives on the left-hand side, so we're going to swap that sign out in just a second. So that one will be a negative 0.54 if we round it off to the nearest hundredth, and the iron one, remember, was a positive 0.77. So let's add these together. Looks like we have to double this one on the bottom, so that the electrons lost equal the electrons gained. So now I have 2 lost and 2 gained. Okay, so now the electrons cancel out. And for that, when I do that, I end up with 2I negatives plus 2 Fe3 positive, produce I2 and 2 Fe2 positives. So I have 4 positives on the right-hand side, 6, and yeah, the charge balances. So now I can add the potentials together, and I get a negative 0.54 plus a positive 0.77. So that gives me a potential of positive 0.23 volts. Boy, that was sort of a tough one. All right, well, let's see if you can do the next one on your own. Go ahead and try letter B. Pause the video. Come back and we'll see how you did, Kay. All right, welcome back. Looks like we have Sn is becoming Sn2 plus. To do that, it had to get rid of 2 electrons. The other one is Ag plus is going to turn into Ag, and to do that, it had to gain an electron. So let's see if we can find both of those potentials on the other page. So let's look up the reduction first. Ag plus an electron makes Ag. Ag plus an electron makes Ag. Here we go. Zoom in so you can see that. So it looks like that's, I'm going to call that Ag plus a 0.80. I know it's 0.7996, but we're going to leave that as a positive 0.80. So let's go ahead and write that in here. Positive 0.80 volts. And then my tin one, now this is oxidation, kiddos, so we're going to look for the backwards reaction and change the sign. So we're looking for Sn2 plus 2 electrons making tin, and we're going to change that sign. So Sn2 plus 2 electrons making tin. Oh, we used that earlier on a video right there. Now that says negative 0.1375. We're going to write that down as a positive 0.14. Remember, we're changing the sign because it's the backwards reaction. So that's a positive 0.14 volts. So it looks like my potential is going to be a positive 0.94 volts overall. And my overall reaction, I have to double this one here. And it looks like I have Sn plus 2 Ag pluses make Sn2 plus and 2 Ags. How did you do? All right, getting the hang of it, eh? All right, go ahead and try the last example. Pause the video, then come on back and we'll see how you did, okay? All righty, looks like Zn is becoming Zn2 plus, and to do that, it has to get rid of 2 electrons. And it looks like my cadmium 2 plus became cadmium, but to do that, it had to gain 2 electrons, didn't it? So let's look this one up first because that definitely is reduction. So cadmium 2 plus 2 electrons is what? Let's see, cadmium 2 plus. I think we've used that one already somewhere. Maybe we didn't. Cadmium 2 plus 2 electrons makes cadmium. It's right here. All right, so that's a negative 0.403 volts. So let's go ahead and write that down directly because that one, we don't change the sign on, that was reduction. So that's negative 0.403 volts. And the other one is going to be the zinc 2 plus 2 electrons becoming zinc. We're going to change that sign because this one here, kiddos, is oxidation. So zinc 2 plus 2 electrons make zinc. Let's see if we can find that one. I think we've used that maybe on a previous video. So here it is. It's right there. Zinc 2 plus 2 electrons make zinc. Now that's negative 0.7618, but we're going to have to change the sign to a positive 0.7618, and we'll round that off to the nearest hundredth. Okay, kiddos? So this one is a positive 0.76, and now let's round this other one off here to a 0.40. All right. Let's write the overall reaction. We should be pretty good at this. 2 electrons lost and gained cancel perfectly. So we end up with zinc and cadmium 2 plus makes zinc 2 plus and cadmium, both the atoms in charge balance. Then I can add my potentials together. I get a positive 0.36 volt battery. Okay, how'd you guys do on those? Yeah, it takes some practice. We'll do a few in class, and you guys all agree with me that it's really not that bad. All right, thanks for listening. We'll see you soon. Bye-bye.